In the previous videos on linear algebra, we've been looking at systems of linear equations and putting them into the form of a matrix. And in particular, we've been putting them into triangular form. In this video, we're going to look at additional forms for matrices, and we're going to look at specifically echelon form and reduced echelon form. So both reduced echelon form and echelon form are going to make our job a little bit easier when we're looking at the solution set for a system of linear equations. And we can expand on what we already know about putting matrices in different forms. So before we've been putting them in triangular form. And we can say that a rectangular matrix is an echelon form if it has the following properties. So 1, all non-zero rows are above any rows of all zeros. Property 2, each leading entry of a row is in a column to the right of the leading entry of the row above it. Number 3, all entries in a column below a leading entry are zeros. Here the leading entry is the leftmost entry, so the leftmost non-zero entry of a row. So if a matrix has those previously mentioned properties as well as the following, so as well as the next two, it's a reduced row echelon matrix. So it's in reduced row echelon form. So the fourth property and the first property of a reduced row echelon form matrix is that the leading entry in each non-zero row is 1. Then the next property, so the second property for a reduced row echelon form matrix, is that each leading 1 is the only non-zero entry in its column. So generally, if you're being asked to row reduce a matrix, then you're going to want to find the echelon or row reduced echelon form U of matrix A. So you want to find the row equivalent matrix U of matrix A, which is the one that you probably started out with. And following those 5 properties that I just mentioned, we want to find the positions in a matrix that have leading ones in reduced echelon form, or pivot positions. So that's what we would call a position with a leading one, is a pivot position. And a pivot column is a column that contains a pivot position. So let's start out by row reducing matrix A to echelon form. So the first row of matrix A is 0, -3, -6, 4, 9. Row 2, -1, -2, -1, 3, 1. Row 3, -2, -3, 0, 3, -1. Row 4, 1, 4, 5, -9, -7. And there's no need to memorize all the properties from before. I'm going to bring them back up when we're going through and doing the row reduction. So in other words, you don't have to memorize them because after you do the example, it should come as second nature when you're doing it just because it makes sense. So from that matrix, we want to make the top leftmost entry. So that is A1, comma 1. So the entry in row 1, column 1 equal to 1. So in order to do that, let's interchange row 1 and 4. And then we want to add 1 times row 1 to row 2, and then 2 times row 1 to row 3. And the reason we're doing this is because of the property 4. So the leading entry in each non-zero row is 1. That's from property 4. Because if you take a look at the original matrix has a 0 in the leading entry on row 1. So we've interchanged that with row 4 because row 4 already had a 1 in its first entry. So it's just more convenient that way. So that was the first manipulation. Then, like I said, we're going to add 1 times row 1 to row 2, and then 2 times row 1 to row 3. And this decision is guided by property 3. If you remember, property 3 said all entries in a column below a leading entry are zeros. So we added 1 times row 1 to row 2, and 2 times row 1 to row 3, so that we could make all of the entries under that leading 1 in row 1, 0. So in the next step, we want to do the same thing for the second row. So we want to take entry row 2, column 2, and we want to make that 1. So from the manipulations from before, we're going to start out with the first row as 1, 4, 5, -9, -7. Next row, 0, 2, 4, -6, -6. Third row, 0, 5, 10, -15, -15. And row 4, 0, -3, -6, 4, 9. And this is what we're starting with. And now our objective is to make the entry in row 2, column 2, we want to make that equal to 1. So now we're going to scale row 3 by 1/5, and then we're going to add -2 times row 3 to row 2, and 3 times row 3 to row 4. And then we're going to end up with, in the first row, we have 1, 4, 5, -9, and -7. And then the second row is all zeros. Third row is 0, 1, 2, -3, -3. Fourth row is 0, 0, 0, -5, 0. And then we're going to interchange rows. So we're going to interchange row 2 with row 3. And now we can see that we've got pivot positions in columns 1, 2, and 4. I think in the video it says 1, 2, and 3, but it's 1, 2, and 4. So you can see in row 1 we have the value 1 in the first column, and then row 2 we have the second entry, and then in row 4 the leftmost value is -5. Now we're going to talk about how you can use reduced and echelon form, so reduced echelon form and echelon form, to understand the solution set of your system in simplified terms. This time we're going to look at a different matrix. So say we have a matrix that has been row reduced already, so it's been row reduced to reduced echelon form. So the first row is 1, 0, -5, and 1. Second row is 0, 1, 1, 4. And then the third row is all zeros. So that corresponds to a system of linear equations that is x1, 0, -5 times x3 equals 1 as the first equation. And the second one is x2 plus x3 is equal to 4. And then the third row is just all zeros. So the variables, the stand-in variables here, x1 and x2, are going to correspond to pivot columns. So x1 and x2 are the pivot columns in the matrix and are called the basic variables. And the other variable is a free variable. So x3 is not a pivot column. Okay, now that we've identified which variables are in pivot columns, we can now describe the solution set by finding the basic variables in terms of the free variables. And just to state this again, x3 is not in a pivot column. So x3 is a free variable. We can write whatever we want for x3. So x1 is equal to 1 plus 5 times x3. x2 is equal to 4 minus x3, and then x3 is the free variable. Now that we have everything written out in terms of x3, we can have our choice of x3. So whatever choice we have for x3 determines a different solution of the system. And every solution of the system is determined by a choice of x3.